Now what I'm going to do is instead of directly answering this problem, I'm going to switch over to a pendulum problem, and you'll see that the physics is actually the same. So what we have for the pendulum is tension. What we have for this problem here is a normal force. So the expressions will come out the same, but I thought that it would be good to go over a different example. That way you guys can have different points of view in terms of seeing different problems. Because what normally happens is if I only do this and then give you a pendulum problem, you'll say, well, how are they the same? So I want you guys to see that they are the same. That way you don't panic on that. All right, so let's go ahead and look at a pendulum. So a pendulum is just some type of object that's connected to a string. So it could be a rock, it could be a toy, it could be a spicy chicken sandwich. Whatever you want to tie to a string and have it swing around in a vertical circle, okay? So this is not a top view, this is a side view. So we're going to try to figure out how a pendulum experiences circular motion. And specifically we're going to look at how can we determine the tension at both the top and the bottom of this motion.
This is a side view, you said?
This is a side view, so we're watching somebody swing whatever you want on a string in a vertical circle. Again, this will be the last page for our centripetal force notes.
I never agreed with I never believe what this fool is ridiculous.
That's more you have to.
So you told me yesterday there were like 3 new videos.
Alright, so we have 2 cases here. One where the ball or object is at the bottom of the path, and one where the ball or object is at the top of the path. So let's go ahead and look at the first example. So we have our object, and I'm just going to make a point mass. And I'm going to draw a free body diagram. Now, what forces are acting on this point mass when it's at the bottom of the circular path?
Gravity.
So gravity, which points
Down.
Fg. And what other forces acting on it? Are there any other forces?
Natural force.
Oh, there was centripetal force.
So there's the centripetal force.
I'm going the opposite way.
Okay.
Want to be going inward?
Yeah,
We'll say that's
inward.
Fc, but what is physically responsible for that? Because again, the centripetal force is not a force by itself. There's some other force that we're labeling. The tension.
Isn't the force of gravity part of this centripetal force at a certain point?
Yeah, so that's what we're going to see.
Or you just throw your fire there.
Okay, so we have the tension there. All right, so if we were to find the sum of these 2 forces, right? So we find the sum of the forces. Let's see that that is the tension force. We're going to say that that's positive, and then here Fg is going to be negative.
Where'd you put some of the force in there?
I just added that a bit. It's redundant. Now, before we used to see problems like this, and if there were 2 vertical forces, we just said, oh, there's no acceleration, it's 0, and so the 2 forces cancel out. But in this case, that is not true. So there's going to be some acceleration that we have.
What's the gravity figure?
So now, as Keller was pointing out, he said, well, isn't gravity a part of the centripetal force? And that is true, that's correct, it is. So this sum of the forces is actually equal to the centripetal force. Because the centripetal force is the net force in the radial direction.
Which
Okay?
way?
And the radial direction is pointing towards the center of the circle.
FC equals some forces.
So Fc is equal to T minus Fg. Fc can be replaced with MAC. So if we wanted to solve for the tension at the bottom, we say that it is equal to MAC plus Fg equals the tension.
And why would that be at the bottom? How do you know that would be at the bottom?
Because we started off with saying this is at the bottom. And we can replace AC with something that we can measure,
Velocity.
which is going to be V squared over R. Fg is just going to be mg. And this is going to be our expression here. So that's for the tension at the bottom.
You're gonna leave it and MAC plus FG would be a problem.
It's not that it's wrong, but AC is something that you can't directly measure. You can measure the tangential velocity, but you can't directly measure AC. All right, so let's go ahead and take this guy, because this is the solution for the top or bottom. And let's go ahead and look at the top. Now again, I was telling you that I wanted to outline the general process. So what would be the process here? If you were to look at this, what would be the steps that we would take?
Body, then I draw the diagram of the facing.
Okay, so first we draw a free body diagram. So let me go ahead and draw the free body diagram for the top. So there's that same object again. Now what forces are acting on the top of the path? Gravity, which is pointing up.
Going down.
You never know. So we have Fg. What other forces are acting on it? Or are there any other forces? So tension in the string,
It's also going down.
that's also going down. I'll use green because they're going to be right next to each other.
Couldn't you just put FG plus C?
Yeah, but the free body diagram, we have to identify that. All right, what was our next step that we did?
Some of
Some
the
of the
forces.
forces. Bonus question, where does the sum of the forces come from? What is that?
Centripetal force.
Who thought of that idea?
Newton.
Newton.
Second law.
Newton's second law, that is on top of things. So Newton's second law tells us we take the sum of the forces.
I just see it everywhere.
And what forces do we have here?
Tension and force of gravity.
We have tension and gravity, and both of them are pointing down. You can either say plus or minus, you're going to get the same thing. So we'll just say plus, but just know that they're in the same direction. If we put minus over here, all it's telling us is that our centripetal acceleration, negative-wise, is pointing down towards the center. All right, so we set that equal to our centripetal force. Then we have T plus FG. This becomes MAC. And then if we want to solve for the tension, we have MAC minus FG equals the tension. This is going to be mv squared over r minus mg equals T. So if we were to swing an object around in this circular path, and we know that the maximum tension that the string could experience is 50 newtons, at what point would you expect the rope to break?
And it's more than 50?
So process that. So again, we have a physical string or chain or something. We go to Home Depot, it tells us that it can experience 50 newtons of force. And we want to know at what point, if we're swinging some object around, at what point is it going to snap? So talk to your neighbors. Now I'm going to check to see what you guys think.
At the bottom.
Then the other side of the equation.
So he's asking at what point would the string break?
Yeah.
The tension at the top is always lower than at the bottom. So I'm guessing when tension at the top is higher than 50?
Yeah, because when you're swinging it up, it's not exactly, I mean, because since gravity's pulling it down, there's slack. There's going to be slack because the ball's going to want to come down, so it's going to create slack. So I'm guessing it would be somewhere between the top and the bottom. I think it would be somewhere between the top and the bottom because as you're twirling it, I mean, if it's perfect, then I guess perfectly at the bottom. But if it wasn't perfect, when you're swinging it around, you'd add extra force, so it would be somewhere between
So you put the velocity on one side.
Then maybe at the bottom.
I think it's at the bottom.
Yeah, I'd be at the bottom. Because usually when you're swinging stuff, and you fly up. I don't know.
It doesn't snap with the bends that it snaps where the object is attached.
Yeah. Sorry, I'm gonna stop.